All right, well, let's get started. So just as a quick reminder, so all of the survey data that you put in, there's a really good response rate, so thanks for those who contributed to that. So all of those grades are in for that lecture bonus, so you should see that. There's this other bonus opportunity is that there is a seminar this Friday. It's supposed to be a highly accessible seminar about statistical kind of issues with, there was an issue in the American Statistician that had a bunch of articles related to alternatives to p less than 0.05. And so Dan is going to summarize some of those big issues and some of the solutions that came up in that particular issue. And if you're interested, you can attend, and there's a bonus on here, and this bonus opportunity actually, if you're not available at noon on Saturday, there's still an opportunity to get some of the points on this, because the first 2 points on this 5 points possible are to summarize what Dan says is the main problem and explain what you think are some interesting solutions, but the last 3 points are actually just to find this, the American Statistician issue that is the subject of this talk. You can find that online, and then pick 3 titles that you think are kind of interesting from the table of contents, which you can get access to even if you don't have access to the articles. And so, so that's even available even if you don't attend, but then if you do attend, then you've got these additional ones here. So that's kind of one of the last kind of big extra credit that we have available. Questions?
So in the last point, you just picked 3 articles?
Yeah, it'll say, if you click on the assignment, it'll say in detail, but essentially it's basically, you'll go to the table of contents of this issue and you'll see a bunch of titles. It's actually a pretty big issue, and you can kind of say like, oh, so here are some interesting titles that, and if you're actually on the ASU network, you'll probably be able to read the articles if you're interested. But I just basically want, for extra credit, to at least have you to put your eyes on the table of contents and look down through and see how some of the pros think about p less than 0.05. So that opportunity is coming up. Then today's lecture is picking up, it's the last half of VRT, Variance Reduction Techniques. So just quick announcements, there's only one more kind of technical Canvas activity before the review Canvas activity. It's due before Tuesday. There are no more homeworks. Aside from, there's one that's still, I think, out, that's due either tonight or tomorrow. No more labs, just any more the lab spots are just available there for Open Lab, so for final project modeling help. For the final project, just general questions to keep in mind. I guess the second one first, we're not looking for like an actual capstone project or something here. You're picking a small scoped project that you can accomplish in the short period of time, but you do want to make sure that you're not just, validating a queuing theory result or something. So if you find that you're saying, well, in our simulation, we're just sort of confirming that when you add another server, the average wait time goes down, we don't really need a simulation for that. Now, your as-is system might be just as simple as that, and then you just have to validate that a simple simulation model of an MM1 queuing node actually matches the data. But then where the complexity will come in is saying, well, then what am I going to do for my intervention model, for my, my proposed change to their operations? Am I going to reorganize the way the workers are allocated, the way things flow through the system? And then you can justify why you need to use a sim. It wasn't to verify the as-is model. The as-is model was just there to sort of show you got the numbers right to match the real world. And the sim is there to then allow you to play with it in a way that you can't go out and play with the real world. And so that's one opportunity. Or if you don't necessarily want to do like here's a way you can change things, if you do have a more complicated as-is model, then maybe your sim is just demonstrating that, well, they're not quite sure which of these 3 points are really the weak point in the system. So maybe we'll just build one type of the system and we'll experiment with these 3 points. Maybe we'll induce a bottleneck, or we'll leave a bottleneck and we'll see what happens to the system. So just a better understanding of the system that would not easily be possible without a tool of simulation. If it's something you look at and you kind of already know what's going to happen, then maybe you need to add a little bit of complexity to it. But I'm not asking for a lot. It's just enough to make it a little confusing without ever having to actually do the simulation. So you'll do that, and then you'll present on it. 10 minutes of presentation, 3 minutes of Q&A. We'll do that during the lab, your normal lab section. You only have to go to your normal lab section. And then there's a project report that'll be due this Saturday. This is just before finals week, so we present the Wednesday before finals week, the last week of class, and then you'll have that report due that Saturday, and that'll be it for the final project. There is an optional thing is if you'd like to upload your presentation. I don't have a great cache of presentations to put online as examples for what people's final presentations look like, but I'd like to build that up. And so I have a Canvas activity that's totally optional that if you want, you can upload the presentation materials you use so I can start to build that up for future iterations. But it's no grade for that, and you can totally skip it if you'd like. On the other things, there's a lot of final exam review practice and review activities out. So there will be, or there is already a Canvas activity M, which is one of these ones that it has a higher point total. You can take it as many times as you want. It iterates through all of the other Canvas activities, drawing randomly from them. Then there's lecture M, which is not this upcoming Tuesday of Thanksgiving week, but it'll be the week after that, and that's the final exam review lecture. And then there are these practice ICAs. So once that ICA disappears, it will show up as a practice ICA after Lecture M. And there's already a pre-midterm practice ICA available if you want to review any of that pre-midterm material. On Canvas, I've got example final exams from previous semesters, as well as at least one solution set. The first couple semesters I taught this class, I just graded without a key, and so I don't have keys for that. But then I made a key last semester to make it, to anticipate, coming up to semesters like these. So there's only a key available for the last exam, but there's 2 other exams before that you can look at and compare to. And if I get a chance, maybe I can put together a key for those if that seems like that might be helpful. There's a couple extra problems from the book, as well as some solutions there. So there's a bunch of those resources. And then the final exam has this retake structure. So I just want to make sure everybody knows this ahead of time, so that the last lecture of the class, so during the last week of classes before exam week, in this room on that Thursday, we will have the first shot at the final exam. And then if I can get things back from Scantron quick enough, you'll have your scores back, similar to the midterm. And then you'll have a second shot at a very, very similar exam, very much like the midterm setup, that'll be during the actual slot during finals week, which I think is Tuesday morning. So if you don't want to go to one and go to the other, that's totally fine. We just take the highest score of the 2 of these. If you want to go to both, that's fine too. But so there's no difference between these 2. The content will be slightly different, but the difficulty is designed to be similar. And I will use the same procedure that I used when making the midterm. So for those of you who took both midterm versions, hopefully you felt that they were kind of similar, although every question is very different. And so hopefully I did an okay job at that. I'm going to try to do the same with the final. Although, because it is 75-minute, things will be concentrated more on the second half of the material. I have the post-midterm, but I am going to integrate some stuff from the early stuff. So do expect to know what a model is, like know what the qualitative definition of a model is, know about hand simulation, know how to generate random numbers. Some of the stuff that we're doing now talks about different ways you can use the random numbers you've generated. So I might combine those 2. So you might have to generate a random number using a random number generation technique you learned pre-midterm, and then use some of the techniques we've talked about this week and actually making use of those numbers. And so as an example how I'll kind of mix the 2. So the goal is comprehensive, but of course, because it's 75 minutes, it's probably going to be more biased towards post-midterm. And I think that's it for that. We're trying to get lead on the TAs to get the rest of the labs graded. I'm going to probably start helping with that so that we can speed that up, so that you have a better idea of your scores going into the last weeks of the class. Question?
So regarding the finals, so it's the same like amount of material, just that the first one will be shorter, and then the second, like the retake, like the final retake, would be like the same 2 hours? Or
Well, no, they're both 75 minutes. So I want to make these, the exam and the retake are designed to be identical. They're just like the midterm. So if you decide that you don't want to take one, there would be no fault in that. It's not like if you didn't take the one on Thursday, then on Tuesday you've got to take the longer one. So they are really meant to be replacements for each other. They're not going to be, just like the midterm, they're not going to be exactly the same questions, but basically when I go through and make the exam, I'll have whatever, so the midterm I have 31 questions. So let's say I have 35 questions. I'm going to say question one, I'll have a one-word document of writing it up, and then I'll come up with a question one that I think is nearly identical, and I'm just going to go down through there, and then the left one will be what we see on Thursday, and the right one will be what we see on Tuesday, but both designed for 75 minutes, covering the same topic material. Yeah?
How many cheat sheets are we allowed?
Oh, it's same number cheat sheets of the midterm. I know some people say, well, since I got 2 for the midterm, maybe I should get 4, and maybe that'd be easier because since I already made my 2, then I can just add on to my 2. But I think ideally, I think the 2 was maybe a little more than I would normally give for the midterm. In fact, that might have originally been a typo that I just left in for several semesters. So, and I do believe, and I think there's studies out there that show that making the cheat sheet is a valuable studying activity. So, so I understand the argument that it would be much more convenient if I could just let you just take whatever you currently had and add on to it. But I am going to challenge you to keep it under the same length, so the 2, but front and back. So if you want to use one that you already had, that's fine, but you still got to keep it to 2, front and back. Any other questions? Yeah.
You're gonna try to have the grades in like a couple hours after like the midterm, or is it gonna be like a couple days later?
Well, so yeah, good question. So I mean, what happens is we package them up in an envelope. I drop them off at the library, and then it kind of depends on the lead time back from the testing center. So once I drop them off, midterms are usually can get back really quick. I mean, I was surprised I dropped them off at noon and I had them by 5 p.m. But this time of year, because a lot of people do their second midterm that week too, it gets a little backlogged. And I am also traveling that weekend. They deliver the results to me electronically, so I still will be able to post things even if I'm traveling. But I can't guarantee a lead time on that. I know that ideally it'd be great if I got it back Friday and then you could say, well, this is the only final, then maybe I don't have to come to final exam week, or maybe, and I appreciate that, so I will work as quickly as I can in getting that back to you, so those of you can try to short circuit travel arrangements and things like that, but I just can't guarantee that.
Appreciate it.
Any other questions? Okay. All right, so this is sort of the last major technical content of the course. We'll kind of do an overview of this content and add a little more application-specific stuff on Tuesday. But these are sort of the last kind of tools that are going to be the sort of important things in the toolbox here. And so we've been summarizing this week these so-called variance reduction techniques, which are otherwise known as VRT in the field, for simulation. And so variance reduction techniques are basically incorporating more of what we call design of experiments into simulation studies. And so we are trying to add additional controls, where control is the statistical term for accounting for other sources of variance. We know we have variable outputs from our simulations, but some of the variability isn't interesting variability. It's just the fact that the inputs are variable. So we want to know that when we're comparing 2 models, or when we're trying to make an estimate of performance of one model, then is there a way for us to really just focus on the variability that matters as opposed to just random input variability? And so we cover 4 of these methods this week. There are a whole lot more of them. So we covered these 2 last time, which I'll briefly summarize, CRNs and control variates, and we'll pick up antithetic variates and importance sampling. Especially these 3 here, common random numbers, antithetic variates, and importance sampling, are used a lot in Monte Carlo methods. So if you do Monte Carlo sims, we've done a lab where you estimate a pi with Monte Carlo sims. If you do a lot of that, these are great ways to reduce the number of Monte Carlo simulations you can run. And I'll show examples of those. But you can also use them for discrete event system simulations like we've been doing. So we said for common random numbers, we've seen this a couple of times this semester, and we're just kind of formalizing it. The basic idea in common random numbers is I choose two simulation models, I run them with the same number of replications, and both simulation models use the same random number seeds for paired replications. So replication 1, they both use the same seed. Replication 2, they both use the same seed, and so on. And that generates effectively the same inputs, the same random inputs to both systems, so that when I subtract from both systems, then I end up only seeing the difference between the systems for that similar input. It's like an apples to apples comparison, as opposed to just seeing variance that comes out of the fact that one model happened to get one set of inputs and the other model got a different set of inputs. And so mathematically, we say that by introducing covariance between two model outputs, then we go from having the independence variance measure, which is just the variance of one model plus the variance of the other, and then we actually can subtract off a term related to their correlation, related to their covariance. So if we can make two models vary the same, so if we have two models, a model of a bank, and we have a model of a bank with operation 1, a bank with operation 2, if we can say that in both of these models, if I put, say, a big burst of traffic right at 9 a.m., followed by not much traffic after that, that puts a strain on both of them, so that both of their wait times go up due to that burst of traffic, then I say that, okay, that's great, then there's an opportunity here for me to reduce the variance in the comparison between the two, because they both seem to be stressed out by the same types of inputs. So for every type of input, I just look at how differently they're stressed. And so I can kind of summarize that here, where if I have, and this is data from the lab 2 from the muffin sim, but this could also be those banks. This could be the bank under one operational strategy, the bank under the other operational strategy. Without pairing the inputs, then I just get a bunch of data from this bank model and a bunch of data from this bank model, and I see a significant amount of overlap. So if I just took an average without doing a two-sample t-test, it may be that this strategy has a larger value of the output on average than this one, or I might have just gotten lucky or unlucky, however you view it, and the sets of inputs that were drawn for this strategy just happened to have more that were under the average, and this one happened to have more that are over the average. So we have two sample t-tests to help us deal with this variance thing. But the idea is that if we can pair their inputs, then it allows us to see patterns that may be even stronger. And so if I pair the inputs to know that everything along this line comes from the same input, then I know that for this input, it had a larger performance measure, and if I look across inputs, the slope of these lines are always positive. So now I know that even though there's overlap in the performance here, I don't care that much about the overlap. I more care about the fact that these points kind of correspond to these points down here, and these points correspond to these points here. So there really is no overlap, because when you kind of just look at where the individual inputs are, for every input, this one is a larger number than that one. So I can either plot these paired experiments like this, which is very common, or if I have a very few number of inputs, like in this case, we had 10 different batches. So we had muffins that arrived for one student in the lab, muffins that arrived for a different student in the lab, and so on. I can plot them this way, where I've got my 10 batch schedules here, and I can say for this batch schedule, the greedy policy is down here, the nearly full is up here. So the red filled circles happen to always be on top across all the inputs, and then the open blue circles are always on bottom across all the inputs. So I can see that although there is significant variation in the outputs, if I just look at them relative to the inputs, if I control for the variance in the inputs, then I see a clear pattern where it is always the case that the nearly full policy has a higher value of the performance measure than the greedy policy. And so that is the advantage of these common random numbers. And so that allows us to turn a two-sample test into a one-sample test, where we're just going to compare each one of these differences to 0. And if the confidence interval that we get across all of these differences is is far away from 0, then we can conclude that the differences are far away from 0 and one is always greater than the other, at least to statistical certainty. And so here's an example they did in the book. This is very similar to the example I just showed you that ran 100 replications of 2 different models. The models were simulating an MM1Q and an MM2Q. So these are things that we know from 470 that the MM2Q should have a lesser wait time because there's more servers running. But we still see a huge amount of variance. And if we just, effectively now the pairings are arbitrary. So even though these are drawn as being paired together, the input that went into one is different than the input that went into the other one. So I could have sorted these any way I wanted and paired them up, and the pairing doesn't do anything for me. But if I do pair their inputs together so that every queuing model gets the same arrivals, then now and take their differences, then I do see consistently that the MM1Q, the filled circles, are on top of the MM2Q, the open circles. And there's a very small effect. And if I go back and look at the variances, that effect would be very difficult for me to see if I did a 2-sample t-test. Because if I were to go back to, say, a plot like this for their data, there would be a huge overlap because the effect is not very big. So, but here, I can see that the effects, although they're small, they're very clear. And if I were to generate confidence intervals here, then this would almost certainly be bounded away from 0. So that's the magic of these common random numbers. How do you implement common random numbers in ARENA? So you go back to, remember we talked about random number generation, and in ARENA you can drag on this seeds element and double click into it, and you can add an input stream, and you can create either a named input stream like this one says, inter-arrival stream. In this projector I can't read what I wrote because this is the third one there, but you can even also just put a number there. So if I put 10, that's the default random number stream. So by default, ARENA takes from 10. And so if you edit 10, you're editing ARENA, all of your model, without making any changes to the model. And then under seed value, you can leave it blank, but then under interface option, initialize option, you change it to common. And what common does is summarized down here, is that every replication will start with a seed that is 100,000 more than the previous replication. And that guarantees that if you run multiple models, then they're always going to have consistently replication 1 will have a certain seed, replication 2 will have another seed, and so on. So you can open up ARENA as many times as you want with as many models as you want, as long as you've initialized the stream to common, then you then get paired replicates that you can then run a paired t-test in the output analyzer. And so if you don't use default stream 10, if you instead use like inter-arrival time stream, the name that I put in the last one, then you can go into your model and everywhere where you draw a random number, you add an argument to the end of the random number here. So if I go here, if this is normally expo 5, if I do expo 5 comma, whatever comes after the comma, the last argument in the random number stream, after all the parameters. So if this is a 2-parameter distribution, it would be like norm, mean standard deviation, and then if I had a 3rd parameter, that tells it which stream to draw from. So you can have certain random number generators use these common random numbers, or certain random variates use the common random numbers where other ones don't. Generally, if you're just trying to pair all your replicates together, it's easier just to use 10 and don't worry about this. But in principle, you can actually give each, every time you do a draw, you can tell it to use a different stream and you can name that stream. So that is, the downsides of this is that it doesn't always work. So if you ever want to use common random numbers, it's important for you to run a little pilot study where you run your simulation without the common random. So you run your simulation sort of pretending like these are independent replications and you analyze the variance of the two, and then you take their difference and look at the variance of that difference. And if you compare the 2 variances added together to the variance of the difference, then that will tell you if common random numbers will actually work. And so If you end up getting a decrease in variance, you should continue on with common random numbers. But if you don't see a decrease in variance, that means that your two models are probably so dissimilar that pairing the inputs isn't a useful thing to do. That would be like one bank that's optimized for bursty traffic and the other bank that's optimized for smooth traffic. Then it might be that in one bank you thrive on one input that kills the other one and vice versa, in which case this would not be good to pair them together. But if they have a similar result qualitatively to the same input, then you want to use the pairing, and that will get rid of the variance due to the inputs. So that's CRN. Are there questions about common random numbers and this general approach? It's easy to do in ARENA, common random numbers, and the paired t-test is even the default option in the output analyzer if you do a t-test between models. There are, if you get into more advanced statistical courses, there are versions of, say, the ANOVA that allow for pairing of inputs in the same way, and they actually make your ANOVAs have much more statistical power. It's outside the scope of this class, but basically if you do have more than two groups and you want to take advantage of this, that's possible as well. All right. So the other thing, this example got skipped in slides, last slides. I've added them in to Tuesday's slides, and I've put it in here as well. So this control variance is an idea that, let's say I wanted to simulate some sort of operational change in a solar power plant. So it's got access to the sun, but there also are operational things that happen inside the plant. And I've built a simulation, and I want to study two operational strategies. But so I've got a transient simulation where I'm interested in every day as the sun rises and sets what the power output might be. And so I want to simulate over, say, 100 days and find the average power output per day, something like that. But the problem is that along with my operational strategy, I get variance in my power output also from the sun. So, and I know that the temperature that day correlates with how much sun is available. And so the idea would be that if I know the temperature that day, is there any way that I can use the variance in the temperature to remove variance from the output of my sim so I can better compare my two operational strategies? So it might be that I run operational strategy 1 under certain conditions and other operational strategy 2 under other conditions, and maybe it's not possible for me to pair all of the sun information together. So it might be that I'm actually doing this not in simulation, but on a real power plant. I run 100 days of one strategy and then 100 days of the other strategy, and I know there's going to be differences in the sun from 100 days to the other, and I want to control for that source of variance, so that the only difference between the two strategies is really due to the difference in strategy. So how do I deal with that? And so I'm modeling X here as my temperature. EX is my average temperature. I'm assuming I know that from data ahead of time, and I'm assuming I can measure the temperature on every day that I run the experiment. And then Y is my output that I care about, and I want to estimate the performance measure that is an estimate of the mean value of Y. And so the idea here in the control variance is every day I'm going to look at the difference between the current temperature and the average temperature, and I want to subtract off a little bit of that difference from the output in just the right way so that it actually makes the variance of my output smaller. And the way we do that mathematically is we design what's called a control variant, and it's Z is the control variant, and it is just my output that I want plus some scaled version of that difference that I just talked about. So if this is the average temperature on that day, this is the actual temperature on this day, so this is whether it's a hot day or a cold day. And so I am just effectively either adding or subtracting a little bit of that from my output. If I were to take, do a little math here, I could verify that this variant will have the same mean as my output, so it doesn't add any bias to do this. But I can solve for a value of C. If I take the variance of this thing, I can optimize over C to minimize the variance of Z here. And if I do that, I end up finding this little form down here that says that the optimal value of C to minimize the variance in this variant is going to be the negative covariance, which is something you can measure between x and y, divided by the variance in x. And so if I have that little parameter that I plug into here, and then I then calculate what my variance is going to be in my control variate, I find it's going to be the variance in the output that I want to measure minus this term here. And this is always minus, so this will always work. If there's no correlation between temperature and output, then this will end up just being exactly the same variance as y, no harm done. But if it turns out that the daily temperature does correlate positively or negatively with my temperature, then what this will do is it will actually reduce the variance in z relative to the variance in y. So now, instead of estimating y, I estimate z. So I basically take samples of z. I calculate confidence intervals on z. And those confidence intervals will be smaller, and they will still be estimating the same parameter, the expected value of y that I want. So I've created a new variate that I do all my analysis on, my t-tests, whatever, on z. And that will have less variance than y, and it'll still collapse around the mean value of y. So that's the magic of a control variate. And so if I want to do an example of that in MATLAB, then I can, so rather than generating a large sim, I'm going to pretend that the exponential operator is my sim, and my input is just a uniformly distributed random number between 0 and 1. Yeah, question?
Yeah, going back real quick to the previous slide, why is it that if you have greater covariance, like the reduction is greater?
If I, just because of this, there's a minus here, and so as long as I have larger covariance here, then this term is going to get larger and thus subtract off from this term y. So it's kind of like variance y is the worst case scenario, but if I can make x and y perfectly covary, then I can basically get rid of all the variance in y. So I'm just subtracting off variance. The variance in z is just whatever variance was in y minus this portion, and if I can increase the covariance between x and y, this portion gets larger.
Okay, so like I know it's like because of like how the formula is set up, but or like is it only like just dependent on the formula?
Well, I mean, so this quantifies this general idea. The qualitative idea is just that my output y is in part due to operational variance, but in part just due to input variance from temperature. And what I've done is I've built a model of the input variance here. And effectively what I'm doing is subtracting off that model. And so I could build, effectively I built a linear, I mean this, if you kind of look at it here, this with a little bit of rearrangement is like a linear model of the relationship between temperature and my output y. And so given that C is a negative, what I'm really doing is I'm saying, all right, how well does temperature predict the output? I'm going to take that prediction, and then I'm going to subtract it from the output, effectively removing the effect of temperature so that the only thing left over is the effect of my operational strategy. Okay. So I can experiment with that, do a quick example in MATLAB where I'm again using the exponential operator as a model of my simulation, and my input is just this uniformly distributed random numbers between 0 and 1. I know that they have a mean of 0.5. I would like to figure out what the mean of the exponential is, given that its inputs vary from 0 to 1. Now I can do that in mathematics, so that gives me some ground truth here. So if I take the integral from 0 to 1 of the exponential, then I get this 1.7183. So that's what I'm looking for. So I say, well, for 1,000 replications, I'm going to generate 1,000 random numbers between 0 and 1. I'm going to run them through the exponential, and then I'm going to take the mean and the standard error of the mean, so that's just what this notation here is, and I end up getting 1.7 for the mean and the standard error of 0.0157. So that's okay, but it would be great if I could reduce that variance without running any more replications. So the idea is, can I look for a correlation between x and y that allows me to rerun my mean and standard error and get lower variance? And so I'm going to use the formula from the previous slide, where I basically calculate the covariance and I calculate the variance of the x and y that I measured in MATLAB. So there's the variance, and then this formula effectively extracts the covariance. And so I get the variance and covariance, and I can then plug those into this formula, and I get this constant here. So that tells me that I can then implement this variate, which is just going to be my y values from up there, plus this negative value I solved for, times the difference between the input and its mean. And that is going to give me a new random variable that in MATLAB, if I take the mean of, I get 1.72. And if I then calculate the standard error of that mean, using the same 1,000 replicates, I didn't add any replicates, but now my standard error has gone down to 0.002. So I started with 1.7 with a standard error of 0.01, and now I've got an order of magnitude difference in my standard error, and I'm expecting 1.7183, so I'm much closer to the expectation. So I ran 1,000 replicates in either case, but with a little bit of arithmetic here, I got far less variance. And that's just because of this effect, where I've now modeled the knowledge that I've used the knowledge I have about my input, and I've modeled the input's effect on the output to subtract it away so that I can get a better idea of what the mean is with the same number of replications. So that's the idea behind control variance. And you could do this with like I said, you could do this with a simulation like this power system. You could build a DES simulation of the power system, and you could take the temperature every day and do the exact same thing. And you don't have to do your experiment any differently, except you have to make sure you've taken data on these inputs. All right, are there any questions on control variance? That basic idea. CVs. If that seems like an interesting idea, control variance, again, it largely dovetails into the larger field of linear modeling and generalized linear modeling. And this whole area, this whole VRTs, goes into the field of general linear mixed effects modeling. So GLIMs, GLMMs. So if you go on in statistics, you start working with GLIMs, then think back on these lectures, and you'll realize that common random numbers are something we call like random effect. And some of these other things are things we call fixed effects. And we merge those together to get better and better models and reduce variance. And so all this is sort of the tip of the iceberg, but we're just going to give you some exposure and some tools that you can use, at least for Monte Carlo simulations for sure. Yeah?
Are there guidelines for like when you should use each technique?
Well, that's a good question. So like this technique you can use all the time, but it's only going to work when there's covariance between x and y. If there's not, there's no harm. Common random numbers, like I said, you have to kind of run a pilot study, and depending on how the two models correlate with each other, it either is going to work or it's going to make things worse. So in a lot of these tricks, you run a pilot study and you see if your pilot did any better. And if it did, then you run a bigger study with the strategy turned on. All right, so let's learn some new stuff then. So we've talked about these two, and we're going to close out with these two, antithetic variates and importance sampling. So just maybe to wake people up, let's do an attendance exercise. So, and the question here is, what is in common between replicates in common random numbers? So if I have two models and I'm using common random numbers, what is in common? What do I set the same in every replication? How do I make sure that each replication is paired together across the models? Yeah, so in common random numbers, we create a pairing between replicates of two different models. What pairs them together? What do I make the same in one model or the other in order to create that pairing? If you think about it, I think it'll grow on you. All right, so anybody have a good answer? Anybody who knows it, say it aloud now. Seed, all right, so that's what I'm looking for. I want that we know that every random number generator, that's one of the beauty of a random number generator is it is a deterministic function that is apparently random, but if you start it with the same seed, you get the same set of random numbers. So the beauty of that is if we start replications with the same seed, we're going to seed replication 1 with 50, replication 2 with 75, replication 3 with 80. As long as we have a pattern of seeds, then if we have different models that draw random numbers in roughly the same way, then we can pair them together as if we sent the same customers to them. So in real life, it's impossible for us to send the exact same customers into a bank if we want to test our strategy. But in a simulated bank, we can send the exact same customers through twice. And so that trick we're going to make use of in a slightly different way in this antithetic variance, this first case here. All right, so the motivation here is we got common random numbers, like I was saying, we can pair them by seed, and by doing that, we get this common effect where we can really see for the same inputs, how do these things differ? And so it makes these apples to apples comparisons. Now that's good for a relative performance evaluation. How much better is one model than another? But then the question is, what if I'm interested in absolute performance estimate? I really want to know, what is the mean performance from this one model? Is there any way that I can take an insight like common random numbers and figure out a way for me to reorganize my random numbers in one single replication, or not one single replication, one single model, so that I can get less variance for the same number of samples? And so the intuition here is let's say you've got a simulation and I've got replications down here. And so I run these replications, replication 1, it came up here, 2, 3, 4, 5, and so on. So I get a lot of variance out here. Now I know the true mean is right here. Now I might not know that ahead of time. If I ran a sim, I don't know that. But in this particular case, I happen to know the true mean, like the population mean is right there. So I see that sometimes my replications are above the true mean and sometimes they're after the true mean. Now by the law of large numbers, that sort of says that if I take a lot of replications and then average them all out, the average should be close to the true mean. Which also means that if I get a long string of replications that are above the mean, they've eventually got to get balanced out. And so then you got to go, below the mean. So that's why people, like, if they're really have bad luck for a long string of time, sometimes people say, by the law of large numbers, things have got to get better, right? I mean, that's kind of what we're saying here, is that if you get a string of one, then eventually you should get some of the other, or else the mean would not be here, it'd be over here. And so the question is, like, that's great and all, but the problem is that if I wanted to do fewer replications, it would really be nice if things would balance out sooner. So rather than getting, out of these first 6 samples, 5 of them were above the average, only 1 was below the average. Wouldn't it be nice if there was a way that I could engineer the input to this simulation so that for these first 6 samples, there was always one that was above and then below, and then above and then below. So like if I were to take these same samples and just sort them, so these are the exact same data, it would be much better if this were actually the replication, the output that came out. That I got one here, then I got one below, and then one above and then one below, one above and one below. And then this way, so if I look up here, if I average the first 6 samples, the real average is 7. The average of the first 6 samples is 8.7, way above it, because of there's so many that are overrepresented there. And if I average all 20 samples, it's 7.2. If I just resort them, then now the first 6 samples is very close to the average. And again, the average of all is 7.2. So if there was a way for me to guarantee that replicates, that one replicate is always going to be above and the next one's always going to be below, that would be ideal. But I need to do that in a way that doesn't introduce bias. Mathematically, I can say, well, what if I had 2 replications, A and B, and I took their average? And so I know that the average of two replications is an unbiased estimator of the average of any one replication. So it looks like we're heading in the right direction. If I look at the variance of the average of any two replications, then I see it's the variance of one replication plus the variance of the other replication plus, and then a covariance term. And so the thought here is that maybe if I were to make negative covariance, if I were able to make one replication consistently negatively correlate with another one, then I could reduce the variance in the average over what I'd expect if they were independent samples. And so that's what we're going to shoot for here, is how do I engineer an input to guarantee that outputs are correlated negatively together. And I do that with kind of this graphical summary here. I take a random number seed, which is why I asked you about seeds, and I run it into one of my into one model here, and that generates a bunch of uniformly distributed random numbers that go into that one model. You've done your input modeling, so you know that like I need an exponential, I need a Weibull, I need a normal, or whatever, and you've got all your inverse transforms in here. So behind the scenes, these uniform random numbers are getting transformed in the actual samples you want. Those get pulled down into your simulation model, and that's what produces your output. So really your output, your whole simulation could be represented as like a function h, whose arguments effectively are the uniformly distributed random numbers. And so this simulation function will often be, we're going to say, monotonic in these arguments. What I mean by that is if I were to happen to draw a slightly larger uniformly distributed random number, then I probably will get a slightly larger inter-arrival time, and then that slightly larger inter-arrival time might mean that it gives my resources a break, and I'll get a slightly smaller utilization. And so if I do an increase here, I get a consistent decrease in my output. Or maybe if I get an increase here, I get a consistent increase in my output. But generally, there will always be a pattern where if you increase the size of the input random numbers going in, you're probably going to have a similar sign effect when you come out on the output. There will be this relationship. And if that's the case, we can take advantage of that. Because now that we've run one replication, we can then run a second replication where we get rid of the random number generator. And we just take a copy of all of the uniformly distributed random numbers that we drew in the last replication, and we take their complements. We do 1 minus that. These numbers are still uniformly distributed between 0 and 1. But now, if U1 was really close to 0, 1 minus U1 will be really close to 1. So I have induced negative correlation in the inputs of this simulation model. And the hope is that if the simulation model has this monotonicity to it, then I will get negative correlation between the replications of the sim. So that if this replication is high, this replication will be low, and vice versa. That's the goal. And that is resting upon the hope that my simulation is monotonic. Now, we're never going to test for monotonicity directly, but we're going to do those. You can do those pilot studies like we did with CRN, where you're going to try this approach for a small set of samples. If it works, you can use it for a large set. If it doesn't, you can get rid of it. But the reason it'll work is because your sim could be modeled as a monotonic function. So here's an outline of this strategy then. Run your random number seed into one model, or one replication of a model. It's all one model. But so all the odd numbered replications get the pseudo-random number seeds. Then we run those into the simulation model logic and get one output. Then we take 1 minus those, and we run all of those uniformly distributed random numbers, which did not require running your pseudo-random number generator again, which is good if you have a very costly pseudo-random number generator. And then we run those into the simulation model logic, and you get another output. And then we take those two outputs, and now we can't use these outputs as raw data to generate a confidence interval because they're not independent. We have induced dependence. They're correlated. But if I, just like with common random numbers, I can take them, and instead of taking a difference, I take their average. And the averages from this pair to the next pair to the next pair to the next pair, those averages will all be independent. So I can use confidence intervals, t-tests, whatever I want on this variant here, this antithetic variant. So this variance will hopefully be reduced, and these will be independent. And if I need to run R replications of Z, I still only need R draws from the random number generator. And so even though I'm sort of running the simulation model twice, I'm not actually drawing twice as many random numbers, and that can be very good computationally. But the key point is reducing this variance. And so let's see if it works. So here's a book example where they have a MM1 cube, so even simpler. So they know from an MM1 cube from 470 what, say, and I forget which performance measure here, let's call it the average wait time. And so that's this dashed line here. That's ground truth. They know that for sure. And then they've got replications here, the dark ones and the open ones. And this is just all the odd replications are dark filled circles. All the even replications are open circles. And they've just plotted them this way. So it basically goes 1, 2, 3, 4, 5, 6, so that you get pairs of adjacent replications. Now, in this case, this is without the antithetic variance. This is your stand-old, everything's independent. And so you can see that when you take an average of adjacent replications, you don't get much decrease. So the average is the dark bar. This average does fluctuate around the real mean, but it doesn't really reduce the variance that much from the independent replications. Now, if I use antithetic variance, so that every second replication, every even replication, is using 1 minus the uniform random numbers from the previous odd replication, and then I average those two, then this dark line you can see has a much decreased variance, and it really hovers right around the mean. So here's before and here's after. And so I can decrease the variance by averaging across these negatively correlated samples. And that's the idea. I can also do this in the same sort of MATLAB example. So I'm not going to use control variance this time. Now I'm going to use the antithetic variance and see how it works. So again, we know that the answer I should get for the expectation for the average value of an exponential when the inputs are from 0 to 1 is 1.7183. So I end up taking my 1,000 as before, and here's the same mean and standard error that I got before. But now I'm going to redo the experiment using antithetic variance. So now I only draw 500 uniformly distributed random numbers from 0 to 1. The other 500 I get by just creating complements of those, 1 minus that. And then I create an average where I pair those up together. And so my real outputs of this experiment are just the experiment with the random number generated ones, plus the experiment with the complementary ones, the average of those two. And I can take the mean and standard error, or confidence intervals if you want, and I see that the mean gets much closer to the expected mean, and the standard error, again, goes down an order of magnitude. So this is a way that I've actually used 500 random draws instead of 1,000, and yet I have far, far less variance. And that's the trick there. So the way you implement this in ARENA, it's just like the common random numbers case. You go into seeds, but under initialize, instead of selecting common, you select antithetic. And what that will do is it will guarantee that the odd replications use fresh draws from a random number generator, that the even replications will just remember all the draws from the previous odd replication and then do 1 minus them and run that in. So that when you get your per replication data out, then you can pair up, say in Excel or whatever you prefer, MATLAB, R, JUMP, you can pair up the odd replications with the even replications to create this antithetic variant, which is the average of each one of those pairings, and to do all your analysis on the average, as if those averages were the real output of your simulation. And so that's just what I'm outlining here. Same stuff I showed you with the common random numbers. And so then the output here is I've got all my odd replications and my even replications. I take their averages, and that gives me my true output, and then I can just generate a sample mean and standard error. So are there questions about this general idea of antithetic variance? Reducing variation in a single model by creating correlated pairs of replications. All right, so the last thing then is this importance sampling. So I'll give a much more animated, say, why didn't you do animated now? But I'll give a much more animated summary of importance sampling on Tuesday, where you get to sort of sense my feelings towards Samsung. So if you're here on Tuesday, then you look forward to that. There'll be lots of pictures and of equipment that's blown up due to engineers not thinking about rare events, and a particularly large number of engineers at one particular company. So, but before we get to that, let's get through the boring stuff and what is importance sampling. And so imagine if I want to know, I want to study just rare events. I have a simulation of a nuclear reactor, and I know that reactor does melt down, but I don't know how often it melts down. But I want to know how often it melts down because I want to make sure that maybe that's below a certain threshold. So I say have like, it's catastrophic but rare when a nuclear reactor reaches a certain critical temperature. And so I'm going to build a simulation of my reactor and validate my simulation. And in the validated simulation, I am then going to ask the simulation, how often does the reactor temperature go over some critical threshold? And this is very, very rare. And so the problem with that is that if I needed to simulate it, I would need to simulate a lot of replications. So basically, if I were to put the whole reactor into this thing called sim, and x was my input from whatever the input variation is coming into my stochastic simulation, then this idea here is if I wanted to estimate this probability, then Monte Carlo sampling basically says I run a zillion replications of my simulator. I ask how many of them were greater than the critical temperature, and then I take that average. And whatever that average is will be an approximation of this probability. So if I run 1 billion simulations and 5 of them come up greater than this critical temperature, then I know that a good estimate for this probability is 5 over 1 billion. But the problem is when I do this, I'm going to need a whole lot of replications. And so it may be that I need so many replications that my simulator is going to take 10 years to finish. So is there any way I can, but the downside of that is like most of the time, the simulator is going to simulate reactor temperatures that are not interesting to me. It's going to simulate normal operations. And I would like to I sort of don't care about normal operations. So the idea here is, can I somehow bias my simulation to generate more of these meltdown events than would normally happen, and then somehow correct for that bias afterwards? And the way we do that is we look back and say, well, the expected value of a random variable when you run it through a function is this thing. Now, so it's just the integral over the range of that variable, the support of that variable, times whatever the function is, times the density of whatever that random variable is. So x is my input from my input model, and this is the expected output. Now I can do a little bit of arithmetic under some calculus here, and I basically can say, what if I choose a new input? I want to choose an input that guarantees that my reactor melts down. I don't quite know exactly what that input is, but I'm pretty sure that if I make the temperature that day really hot, then I'm going to make sure I only simulate days when the temperature is hot. Or if maybe I make the salinity of the coolant a particular level. And even though it's outside of normal ranges, I'm going to simulate a reactor that is in those conditions that are really, really bad conditions. And so I am going to say my new random variable represents the input in these really bad conditions. And it's going to have its own PDF, which will have the same range as my normal input PDF. And then what I can do is I can insert it. So I take that same function there, and it's had an f of x here. So I'm going to effectively divide out. I'm going to insert my f of y And that allows me to sort of, this is identical to the expression that's above, but I've now introduced a new distribution, the distribution of the terrible events. I've just added it in there, and I haven't changed, this is still equivalent to that, but I've now had the opportunity to add it in. And that allows me to say, well, instead, in order to calculate my expected number of failure events under normal conditions, I now can alternatively calculate the expected number of failure events under really bad conditions, but then multiply them by a special parameter or special ratio here we call the likelihood ratio. And that likelihood ratio is just the ratio of the PDF of the normal conditions divided by the PDF of the abnormal conditions. And so by doing that, then this provides me a way to run, say, only 1,000 simulations in terrible conditions, and then those will end up giving me a lot of terrible outputs, too many to be realistic. But then I scale them by my likelihood ratio, and then the net effect will end up actually being the same result I would have gotten if I ran 1 billion simulations under normal conditions. So let's see that played out in a little example here that's much simpler than that. Let's say that my simulator is trivial. It's just the identity function. And so my simulator takes a random input in, and it spits out the random output. And I'm going to say under normal conditions, my random input is the normal distribution, the standard normal. And so I would like to know how often my simulator generates an output that's greater than or equal to 5. Now I know on a standard normal, that's 5 standard deviations away. You know, so I guess this is, I should have made it 6, and then it'd be 6 sigma. And everybody would know that number. But it's 5, so it's almost there. So here, I want to know, so an estimate of that using simulation. And so if I try to, so I can calculate that. I know it's going to be this number right here. But I'm going to go into MATLAB, and I will generate 10 million replications of a standard normal. And I will ask, how many of them are greater than or equal to 5? And MATLAB comes up and says, you know, the average value of that is 0. Why is it exactly 0? What happened there? 10 million replications of a standard normal. MATLAB tells me and this turns up a 0 or a 1. This is basically telling me that the average value of this predicate, that the temperature is greater than 5 is equal to 0. What happened there? What does that tell me about these replications? It's not a complicated thing. It's like, you know, MATLAB tells me that when it took an average of these, this turns up zeros and ones. So this is it's 10 million zeros and ones. I take an average of a vector that has 10 million zeros and ones, and I get 0. Why? What does that tell me about how those 10 million zeros and ones? It's all zeros. Not once in my 10 million draws did I ever get an outcome that was greater than 5. So that's a problem, because this is clearly not that. So how do I fix that? Well, what I can do is I can say, well, what if instead I use an input that's biased to be around 5? So I'm just going to make a really bad input that has its mean at 5, same standard deviation. I know the PDF for this input. I know the PDF for the normal input. And so I can calculate this likelihood ratio. It's just the PDF of the standard normal, or the PDF of the standard normal shifted over by 5. And so that gives me this expression if I go through the math here. And so this is my likelihood ratio. So I should be able to use this to create a simulation that has a better result. And so that's what I've shown here, is that now I'm only generating 1,000 of these. Yeah?
Yeah, regarding the likelihood ratio, shouldn't it be the other way around? Because it's kind of like you're analyzing out of how many normal situations, how many abnormal ones would you have?
Well, the form, so likelihood ratio is just something we generally use to talk about anytime you have a ratio of 2 probability density functions is a likelihood ratio. And in this particular one, the reason it's normal over abnormal is that's kind of makes this form of the math work, is that I want to make it so that I get a density showing up here, my new density over here. And so that's the reason why it's structured this way. So I mean, that in that case just does come out of the math, that it's normal over abnormal. All right, so the way I implement this is I generate only 1,000 of my inputs from my biased input distribution. Not that many at all. I generated 10 million from the right one. I'm only generating 1,000 from the wrong one. And then I create my simulation output. So I'm calling it H prime. And like H was the original sim, and H prime is this different one, where I say, well, how many of my abnormal output are greater than 5? And I know that's going to be way more than I need. So then I'm going to multiply it by that likelihood ratio that I just solved for on the previous page. And that will rescale my output slightly. So now if I take the mean value of this experimental outcome, then I get this number. And that number is very close to the number that I was looking at. And I can also take a standard error, and it also shows me that the mean and standard error, and actually here's even a confidence interval. So there's my half width. And so this mean plus that half width is going to include in between there, that's the confidence interval. So the actual mean is captured there. So with only 1,000 replications of my nuclear reactor simulation, I'm able to estimate this extremely tiny probability just by making my inputs pathologically biased and then correcting for that bias afterwards. And that's importance sampling. It's sampling from the important part of the inputs, because you don't really care about the normal operations, you really only care about the abnormal operations. But then you have to correct for that bias afterwards, and that's why you need this likelihood ratio mess. So are there questions about that? About designing your experiment so that you sample from interesting spaces and then correct for that afterwards? And I hope you see the power there, going from 10 million samples to 1,000, and then being able to estimate a number that small. All right. So that's all I've got for you for variance reduction techniques. So we'll wrap up here, and we'll do one last attendance question. And that question is, if I want antithetic variates to work, do I want positive or negative correlation between my paired simulation replications? So if I want AVs to work, so if I want AVs to be good, then do I want positive or negative correlation between, let's say, replications, Y1A and Y1B?
Yeah, listen.